We're going to talk here about section 4.5 in our book, Euler's number. So this Euler's number turns out to be, it just comes up in unexpected places and plays a huge role, particularly in higher math like calculus and beyond. So what we mean by Euler's number, we represent it with E. That's the first letter of Leonhard Euler's last name. He's a Swiss mathematician, and it's a irrational number. So like pi, it is a non-terminating, non-repeating decimal. So it's 2.171828 on and on and on and on and on, and never repeats and never terminates. So we're just going to approximate it. It's nice to think of it as being a little bit bigger than 2. Now, it turns out that mathematically it is we're familiar with a little bit of this notation, but this is a bit of a stretch for us. But one way to define Euler's number E is as the limit as n goes to infinity of the quantity 1 plus 1 over n raised to the n power. So if you put into your calculator, you can experiment with this a little bit. If you do 1 plus, and you can call it 1 over x, and then raise it to the x power, if you put that on your calculator and then go to the home screen, so get out of the graphing menu, and then do stuff like y1 of, and you can try plugging in 1,000, but you have to get pretty big before it converges, we say, very slowly to this 2.171828 and so on. But plug in some huge numbers and see how accurate you can get. You can compare it. If you put up on your screen e to the first, you'll get your calculator's best approximation, and then see how big you have to get better and better approximations. You have to go out there pretty far. So we're going to take a look at this and now revisit this compound interest formula, A equals P times 1 plus R over N to the NT. So as N increases, we know that is the more times we compound it per year, the effective annual yield increases. So the question is, for a given nominal rate, so if you choose, say, 5%, or if you choose 8% interest, annual interest, what is the maximum possible effective annual yield? That is, as you let n get bigger and bigger and bigger, how big can you go? Well, that is a limit question. So what we're really saying is, what is the limit as n goes to infinity of this p times 1 plus? Now we're going to imagine that we're going to take a particular number for r. So we're going to imagine that we pick a value of r, so it's not going to change anymore, and then we're going to try to see what happens here. So this is pretty high-speed math, so see if this kind of makes sense. We're going to make what's called a change of variable, and we're going to say let k equal n over r. So we can see now the r is going to be fixed because we just picked that in advance. Then as n goes to infinity, then the k is also going to go to infinity. So that means we can change our limit equation here that's in white. I'm going to move it to now yellow. We can now take the limit as k goes to infinity. That's still going to be p. We're going to get 1 plus, but now the r over n is going to become 1 over k, because 1 over k, remember, is n over r. That's the same thing as 1 times, and to divide by n over r is to multiply by r over n, so those are going to be the same thing. Then also the raising it to the nt, you can see also from here that n, if we multiply that r over, is the same thing as r times k. So I'm going to write this as k r to the t. So I've changed the variable, and so now the white limit problem becomes the yellow limit problem. Now what we're going to do is kind of pick this apart a little bit here. So this p is just a constant, so it turns out mathematically we can pull that all the way outside of our limit. And so now we can call that p times the limit as k goes to infinity of, now we have 1 plus 1 over k. Now remember, when you raise a power to a power, you multiply the exponents. So that means when you have exponents that are being multiplied, that can come from a power to a power. So that is the k times r times t that we see over here is the same thing as raising it to the k and then raising it to the rt. So the point being that now if you look at this inside part right here, that is exactly what we have said. We just changed the name from n to k. That is going to be e. And so we get the p that was outside times that whole limit thing, 1 plus, I should have said k. Let me go back, calling that was a k and I miswrote it as an n. So that limit of 1 plus 1 over k to the k is just e, and then we still have that rt. This is our Pert formula that you may remember from your Algebra 2 days. So the point is that the most we can get out of a given percent, you pick a particular value of r, say 5% per year. You know that as you compound this more and more, you get a higher and higher return, a higher and higher effective annual yield. So as you compound it 4 times a year, 12 times a year, 365 times a year, if you can compound it an infinite number of times per year, what you really get is e to that rt. It becomes Euler's number. That's pretty remarkable. Now we're going to put that on the shelf and move on down here. Let's graph here on the same axis. Y equals 2 to the x I'm going to do in blue, and then e to the x, and then 3 to the x. So we've done this kind of thing before where we get bases that get a little bit bigger each time. So 2 to the x, when you plug in 0, you get 2 to the 0 is 1. When you plug in 1, you get 2. When you plug in a negative 1, you get a half. And so you're going to get this classic exponential growth function here. There's our 2 to the x. Now e, remember we're thinking of that as about 2.17, so it's a little bit bigger than 2. So at 0, e to the 0 is still going to be 1, so they're going to share that point. But now when x is equal to 1, we're going to get 2.17. It's going to be just a little bit bigger than we were here. And 2 to the e to the negative 1 is 1 over 2.17, which is a little bit smaller than 1 over 2. So as we've seen before, as the base gets bigger, this exponential growth function gets a little bit steeper on the right side of the y-axis and hugs the x-axis a little faster on the left side. 3 to the x will just go a little bit more. So here's 3 to the 0 and 3 to the first, and it's hard to squeeze in there, but that green is going to lie in between the yellow and the x-axis, share that point there, and then get steeper over here. So as we've seen before, e to the x is going to lie in between y equals 2 to the x and y equals 3 to the x. Now there's a couple of things we want to notice here. Because this yellow e to the x is a continuous function, right? You draw it and it's all connected. Then you can pick any number you like. So in particular, you could say if you choose a y value of 2, then come across here, there is some place on that yellow curve. So there is a number k, for example, I don't know what that is exactly, but there is a number k that if you use that as an exponent base e, it will equal 2. Does that make sense? And likewise, you could pick any number you want. You could pick 3. And so for 3, you come over to that yellow curve and come down. There's a different, I'm going to call that L. Then e to some other number, I don't know what that is going to equal 3. But you can do this for any number you like. Pick any number you like. There is e to some power that equals that number. That's an important idea. So what that means then is that this y equals 2 to the x that we looked at, we could figure out how to write that as e to the some number we don't know, k, and then raised to the x is going to multiply the exponents. So you could write And you could also do that. We called this with, I think I did that in green, so let me switch back to green so I stay consistent. Since we could also say this y equals 3 to the x, we could write as e to the some number, I'm not sure what, l times x. The point being, any exponential at all that, come back here, that can be written as y equals ab to the x can be written equivalently as that same a and then e to some letter I don't know, some other number to the x. That is, we can convert back and forth between exponentials of one base to an exponential base Euler's number. That's really an important idea and one we're going to spend a lot of time on. Okay, I'm going to go to the next panel. So here we're gonna talk about annual versus continuous growth rates here. So we are going to, and our book does a really good job of this. Our book is going to say when we just have this y equals a b to the t, then we know that that b is containing that annual growth rate, that percent that it's increasing or decreasing by. And they're going to call that an annual growth rate. Now, we just said that anything that is written in the form a b to the t can also be converted into y equals a e to the k t for some choice of k. We're going to explore that. We're going to see a difference between what our book calls the annual rate versus what our book is going to call the continuous rate. And so you can see annual rate, we get just that basic y equals ab to the t. Continuous is going to be y equals a e to the, and you can see what that r is right there. Think like Pert. That is going to be the percent increase, but it's a continuous rate rather than an annual rate. So these are not the same exact values of 5. They're going to give you different effective annual yields there. Likewise, if something decays, then our b is going to be like a 1 minus r. There's our 1 minus 0.05. And the way we show that with a continuous rate is with a negative exponent. So e to the negative 0.05 t is a continuous rate of negative 5%, or it's decaying by 5%. Okay, so here's the game plan now. We're going to look at this e to the 0.05, and can we write that as an annual rate? So this is a continuous rate of 5%. So when you put e to the 0.05 onto your calculator, you're going to get 1.05127, and it's going to go on and on and on, but I'm going to make this a percent, and I want to keep 3 places past the decimal after I make that a percent. So we can see here that a 5% continuous growth rate is the same as a 5.127% annual growth rate. So here's the difference. A 5% continuous rate is the same as a 5.127% annual rate. Now, to go the other direction, e to the k equals 1.05, we could, graph, the first one is y1, the left side is y1, the right side, so we could graph that as y equals e to the x, and let that intersect with 1.05 and find that point of intersection. I think most of you are familiar enough with natural logarithms that you can do it, I think, a little bit more efficiently here. We haven't really talked about that yet. We will a little bit later, but in the interest of efficiency, when you take a natural logarithm of an exponential base Euler's number, they are inverses. They are going to cancel each other out, and so what we're going to get is the natural log of 1.05, and if you put that into your calculator, you will get 0.04879. And so what we're seeing is that a 5% continuous rate is equivalent to 4.879% annually. That's an annual rate. Okay, so you get a little bit more bang for your buck with the continuous interest, continuous growth rate. Okay, looking at the white one, the population increases from 320 million to at a continuous rate of 2.3% per year, and can we write a formula? So because it is continuous, we know this is going to be base Euler's number. Since we have an initial amount of 320, that is going to be our A. So we're thinking of this as A e to the kt, or if it's easier to remember, you can certainly think of it as Pert. And I think most people remember the Pert, so that might be a little bit more memorable, a little bit easier to wrap your head around. The P, or this little a, is going to be the initial amount, so that's going to be the 320, and the continuous rate of 2.3%, we make into 0.023 the decimal, and that is our equation. And so I'm going to use it as a y, and so here is our equation. So when does the population reach 350 million? Means we're going to put 350 in for the y, or the total amount. That's going to be 320 e to the 0.023 t. We can divide by the 320. This is going to ultimately end up in our calculator. And then we have e to the 0.023 t. Now you could graph both of these and find the point of intersection. I'm just going to be bold here and go ahead and assume that you remember a little bit about how to do your logarithms, natural logarithms. So if we take the natural log of both sides, we're going to end up with the natural log of Euler's number. Those are inverses, and so they will cancel each other out. And so we're going to get the natural log of 350 over 320 is equal to 0.023 t. To solve for t, we're going to divide this crazy number, logarithm of 350 over 320, by the 0.023. And when you do that, we're going to get a value of t, remember, and I think you'll get 3.896 is at least what I got, 3.896. That's a time given in years. So in a little less than 4 years, that population will reach 350 million. Let's look at the next panel. Okay, and here we have now another example. It's a decay problem. So here we have caffeine is leaving the body at a continuous rate of 17% per hour is the time this time. So make sure we note the units. How much is left 8 hours after drinking a cup of coffee with 100 milligrams of caffeine? So we can think of this as our Pert, if that's the way you like, or you could think of it as y equals a e to the kt, either way. So we have then, to start with, if we're doing the Pert, then we have the initial amount is going, well, let's first just get our formula. So it's going to be p e to the, and because it's decreasing at a continuous rate of 17%, that's going to be a negative 0.17 t. So that's how you show decay with Euler's number E as a negative exponent. Okay, so, okay, I'm back. It's my left hand hitting the thing I didn't want to hit. So now we're going to say we're starting with 100 milligrams of, let me bring my pen up here again. So we're starting with 100 milligrams. That's going to be our P. And we want to know how much are we going to have after 8 hours. That's going to be D8. So we're interested in how much are we going to have. We start with 100, e to the negative 0.17 times 100. And so you can put all of that right into your calculator. And I believe if you do that, oh, I'm sorry, I put the 100 in the wrong one. That wasn't 100 hours. That should have been 8 hours. So let me fix that. So that should be 100 e to the negative 0.17 times 8. And what I got was about 25.67 milligrams of caffeine are left, even after 8 hours. It's kind of interesting, I think. So a continuous rate, now next example, a continuous rate of 7% is equivalent to what annual rate? We're going to ask these kind of questions a lot. Can we transition from a continuous rate to an annual rate, or from an annual rate to a continuous rate? So if we have a continuous rate of 7%, that's e to the 0.07. That's what you would get in 1 year. So if you're imagining, your PE to the RT, it's like you're going to plug in a 1 for the T. You don't really care what the P is, whether you want to call that a 1 or just leave it as a P. But we want to know what is going to be multiplying that initial amount after 1 year. So when you plug in e to the 0.07 into your calculator, I believe you will get, and I'm going to round this again after, I'm going to go 4 decimal places here, so 1.0725. And then that, remember, is our 1 plus r, and we're interested in finding this r. So when we subtract off the 1, we have 0.0725 this is our annual growth rate here, and we want to give that as a percent, so that's going to be 7.25%. So a continuous rate of 7% is going to be, and you can think of that as an effective annual yield, or the equivalent of 7.25% compounded annually. And again, that's due to the Euler's number E, right? This is the largest effective rate you could get through compounding if you used 7% annual growth rate. Now we're going to go the other way. So an annual rate of 6% is equivalent to what continuous rate? Well, an annual rate of 6%, we're thinking of that as 1 plus r. That's going to be 1 plus 0.06. That's 1.06. So that's what we multiply by in our, like if we were doing y equals ab to the t, rb would be the 1.06. And we want to know what is the equivalent e to some number k. So we're going to solve that for the k. So you might recognize that we're going to take the natural log of both sides, and when you take the natural log of e to the k, once again we see the natural log and Euler's number cancel, and so we're going to get k is equal to the natural log of 1.06, and I believe that's going to be 0.05827. And we want to give that as a percent, so our percent growth rate is going to be 5.827%. So a 6% annual rate of growth is equivalent to a 5.827% continuous growth rate. Now we'll investigate the same thing but with decays. So if we have a continuous rate of negative 4%, that's a decay. So that's going to be a e to the negative 0.04. And we want to know, we'll just punch that into our calculator. And when we do that, I believe we'll get 0.96079. And remember, this is going to be a 1 plus r, and we want to know what is that r. So if we subtract that 1 from there, I believe you're going to get a negative 0.03921. So negative because it's decreasing, so our 1 plus r, if we had that negative number, that would give us a number that is less than 1, and in y equals ab to the t, a number less than 1 is going to mean it's going to be decreasing or decaying. And so we would give that then as a percent, so we could say either the negative 3.921%, or we could say that it's going down by calling it a 3.921% decay. And finally, let's do an annual rate of -3%, decrease of 3%, decay of 3%, and what's that as a continuous rate? So again, we think of this as a 1 plus r, so that 1 minus 0.03 is going to be 0.97. And so that means we want to know 0.97. Remember, that's going to be our base in this decay function, something that's decreasing over time. And we want to know that's equal to e to what is that k going to be, and can we make that into a percent? So once again, we're going to take our natural log of both sides, and that means that the natural log of e to the k is going to be k. And so when we get the natural log of 0.97, I believe that's a negative 0.03046, if I'm reading that right. So that would mean that our k is going to be either a, oh, it's my left-handedness coming into the picture there, and that's going to be a, I just can't find a good place to put my left hand there, a negative 3.046%, or you could say it's a 3.046% decay. All right. Oops, I spelled decay wrong right at the end. So let me try that one more time there. Decay. All right, very good.